welcome to the mathematics and a new video. Today we discuss following integral from the MIT Integration Bee 2021, and integral is secant squared of square root of x dx. A very interesting integral in my opinion. I want to recall some statements we will not prove. So the derivative of the tangent can be written as secant squared of x. Then the derivative of the square root is 1 over 2 times the square root, and the product rule, okay, in integrative form. And if you want to try this integral by yourself, I give you a hint, and this is add a 0, and keep that in mind to get the result for this integral. I will show how I came up with this stuff. Substitution, I have not tried a way using a substitution. I used this stuff, and I will explain in a second why. So right now it's a good point to stop the video and try this by yourself. Okay, so we will add a 0, and we will do this in a certain way to use the product rule. And I want to explain how I came up with this stuff. Like I said, the secant squared, so without the square root of x, the integral would be the tangent, okay? So it would be nice if there would be the derivative of the square root, and so we would have the tangent of the square root, alright, so with the chain rule. But because we are not allowed to change the integral, and I add this fraction, so I multiply with 1, and why I do this? So this part is for the chain rule, and how to get how to use the numerator is the following way. I tried to add a 0, so here we have secant square root x times 1 over 2 times square root x, and I use braces here, and then we have 2 times the square root of x. And now what I would like to do is I would like to add some stuff and then subtract the same stuff. And how we do this? We do this. This part in red is tangent square root of x, the derivative, okay? And here we have 2 times the square root of x, so it would be useful if we add tangent square root x, and in blue, from the blue part, the derivative, so it's 2 times 2 over square root x, okay? So without the 2 it's 1 over 2 times square root m of x. So the blue part is the derivative of 2 times square root of x, okay? Yeah, and why we do this? Now we have here the product rule. So u prime v plus u v prime, alright? But we added this tangent, so we have to subtract it also. So minus tangent square root x over square root x, so I cancelled the 2, okay? And of course dx. So yeah, what do we have here? Like I said, this is the product rule. So the first part is tangent square root x times square root x and a 2. So this is here, this 2. Okay, this is the first part. And we are left with the integral tangent square root x over square root x. Yeah, so we are left with minus integral tangent square root x over square root x. And yeah, I should also use a 2 here. Why? So this part is done, so we can take care of this part. So I add this 2 for the chain rule, and I write, so 2 times tangent square root x times square root x minus integral 2 times, and this becomes tangent square root x times 1 over 2 times square root of x dx. And now we can see here the chain rule again. So the derivative of the square root is exactly 1 over 2 times the square root. So we can use a simple u substitution. And the integral from the tangent, it's sine over cosine, and this is exactly the logarithmic derivative. So at the end we should get 2 times tangent square root x times square root x minus 2 times the natural log of cosine square root x, and then a plus c if you like. Right, so let's check. Natural log, the derivative is 1 over cosine times minus sine, yeah, so this should be plus, the signs are changing. Alright, so 1 over cosine times minus sine gets the minus, times the derivative of the square root. This is exactly 1 over 2 times the square root of x, so this should be correct. Yeah, alright, that's the integral, the solution to the integral. And just to reiterate how I came up with this idea. Like I said, I know the secant squared integral is the tangent, and because of the square root I tried to force the integral to become the product rule, and hopefully the last term is easy to integrate, and here we were really lucky, and yeah, that's the integral. Hope you enjoyed it. See you next time.